We'll start the topic alternating current, which is for semester 2 physics honors. So here we just follow the syllabus of semester 2 physics honors. Now you should have a basic idea of the AC basically. So what we know is that if we'll take a coil of n turns, okay, and area capital A, okay, which is rotating with an angular velocity omega in uniform magnetic field B, then at any instant of time t, the EMF E is given by E equal to minus d phi by dt. So where phi is B and A into cos omega t. Now this is phi basically, the flux, what we say now. So E is equal to, we'll write B and A omega sine omega t. So this is the EMF. Now what we know is that this E will vary with omega t. Varying this omega t, we'll get the variation in the EMF. Okay. So what we can see is that the induced EMF, it goes on changing through a cycle. Now each cycle will correspond to one revolution of the coil. So the instantaneous value of EMF is generally, okay, it is generally represented by small e, okay, and the maximum value is B and A omega. It is represented by E naught. Therefore this equation it will be now represented as E is equal to E naught sine omega t. So now if it represents a sinusoidal alternating EMF at any instant t, and it will develop an instantaneous voltage V, which is given by V equal to V naught sine omega t, and the corresponding current will be given by small I is equal to, this is small v, small I is equal to I naught sine omega t. This is the alternating EMF current and the voltage rather. So the time of one cycle is known as time period. So time of one cycle is known as time period, and that is capital T. Okay, so the number of cycle per second is obviously its frequency. So if an AC is passed through an ordinary ammeter or voltmeter, okay, it will record the mean value. It will record mean value, okay, for the complete cycle. So in that situation we'll write I bar, okay, say capital I bar, in fact that is the mean value, which will be given by 0 to t I dt divided by 0 to t and dt, which is obviously will be equal to 0 to t is 2 pi by omega, okay, then I naught sine omega t dt by 0 to 2 pi by omega dt, which comes to be 0. So what we can say is that the average value of the EMF for the whole cycle, similarly the average value for the whole cycle will be also will be equal to 0. Since these average for the whole cycles are 0, hence DC instruments will detect zero deflection. DC instrument will indicate zero deflection. Okay, now In AC, the average value of the current is basically defined as its average taken over half the period. So average taken over half the period. Okay, so that is given by I average is equal to 0 to t by 2 I dt by 0 to t by 2 dt, which comes to be, after substituting the value of I and solving it, okay, we'll get 2 by pi into I naught. So this will be the value, which is, we can write 2 by pi into the peak value of current, Similarly, the V average will be 2 by pi into peak value of voltage. Now, what we know is that the AC, it is measured by the strength of the steady current, which would produce the same heating rate. I mean, the square root of the mean square value. Now, what we like to find out the square root of the mean square value. That is the square root of the mean square. So the mean square value is given by I bar square 0 to t I square dt by 0 to t dt. Again, substituting the value 0 to 2 pi by omega I naught square sine square omega t dt by 0 to 2 pi by omega. Okay, and then dt, which comes to be I naught square by 2. So the square root of this will be I naught by root 2, which is 0.707 into I naught. So this is the mean, the root mean square current. Okay, similarly, that is IRMS. This is IRMS. Similarly, VRMS will be equal to V naught by root 2, that is again 0.707 by V naught, which is the peak value. Obviously, what we can say is that when we talk about the household power supply of 200 volt AC, what actually means is that root 2 into 200 volt. Okay, if we'll talk about 220 volt, then it is root 2 into 220 volt, which comes to be approximately 310 volts. So that is peak value of the voltage. Okay, now further we'll just discuss about the, before moving ahead, we'll just discuss about the current potential relation as far as the simple circuit is concerned. So if we take a pure resistor, okay, in this case we'll just put an AC over here, and then the current I is there with the resistor R. Okay, so in this case we just have taken the initial potential difference is V is equal to V naught sine omega t. So the current I passing through it is given by I is equal to, okay, IR, sorry, V is equal to I into R. So now I is equal to V by, this is V actually, V by R, that is V naught sine omega t by R. So V naught by R is written as I naught sine omega t. What we can see is that the potential, applied potential, and the instantaneous, the applied potential difference and the current. Okay, they are both they both vary with sine omega t, and they are in phase. So if you draw the diagram, if you draw the wave for this I and V, so if this is V, suppose, then the current will be something like this. So they are in phase. If this is I, okay, this will be V, this is the time period T. So what we can say is that they are in phase as far as pure resistance circuit is concerned. Similarly, if we take a pure inductive circuit, so as far as pure inductive circuit is concerned, again we'll draw in the place of resistance, we'll just draw the induction coil, and then the source will be there, V is equal to V naught sine omega t, Okay, now what we know is that V is equal to V naught, small v equal to V naught sine omega t, which is equal to, okay, L di by dt. So here we assume I to be there. Here L is the self-inductance of the coil, right? So di from here, di is equal to V naught by L sine omega t dt. So after integrating this one, we'll get I is equal to minus V naught by omega L cos omega t, which is equal to I naught in the place of this into sine omega t minus pi by 2. So here V naught by omega L is the maximum current, and omega L, this omega L, it is represented by XL is equal to omega L. Okay, and this is the inductive reactance. Okay, so this is regarding the pure inductive coil, and what we can find out from here is that the the graph, this is the voltage. Now suppose this represents the sinusoidal voltage V, then this will represent the current I. Okay, so what we can say from here is that the current in the inductor lags voltage by 90 degree. Okay, in the inductance coil, it is clear that the current in the inductor, it lags the voltage by 90 degree pi by 2. Okay, now if we take this the pure capacitive circuit, okay, so if this is C and this is the EMF, again V is equal to V naught sine omega t, I will write Q is equal to CV equal to C V naught sine omega t. Now I is equal to dq by dt. Substituting again the value of this, we'll get C V naught omega cos omega t. So I is equal to V naught by 1 by omega c into sine omega t plus pi by 2. Omega t plus pi by 2. So here this one will be written as I naught and sine omega t plus pi by 2. What we can find it over here is that the current, now in this particular case, the current, it leads the voltage by 90 degree. The current leads the voltage. Voltage by 90 degree in this particular case. Okay, pure inductive circuit. And here if you draw the phasor diagram, what you will have is this. It's a wavy diagram, the sinusoidal diagram. Here you will again see this is V, and in this particular case the current is leading. So this is I. So we have just discussed the very basic of the AC circuits and law related to it. The next lecture we will discuss about the Kirchhoff's law applicable to AC circuit and the other circuit related to AC current. Thank you very much.